to a couple of slightly different problems. So to quickly review what we did yesterday, we motivated the need for post-Hartree-Fock methods for quantum chemistry computations. An early candidate for one of these in applications of quantum computing to quantum chemistry was the variational quantum eigensolver. That basically is a representation of the variational method in a quantum circuit, where you start off from a reference state, typically your Hartree-Fock state. You build up an ansatz to create more correlations between the different parts of your system using some kind of circuit ansatz. And we optimize the parameters to lower the expectation value of the Hamiltonian to try to estimate the ground state energy. We saw these Givens rotations, these single or double excitation gates. I don't think I mentioned it yesterday, but these turn out to be universal particle-preserving unitaries. So if you're looking at something like ground state energy estimation of a molecule that doesn't lose electrons in a given chemical reaction, these Givens rotations are, in essence, all you need to build up any kind of universal ansatz that you want. From this, you can all of these dependent parameters that you can vary to lower the ground state energy estimation. So once again, we have these excitation gates that will take your state from your Hartree-Fock state usually, that populates the lowest orbitals with as many electrons as possible. And then we want to create a mixture of different populations of orbitals in your ansatz. We ended yesterday by creating this graph. So we estimated the ground state energy of the H2 molecule. And we saw that for this simple system, the VQE algorithm under classical simulation, so we just run the circuit on a simulator, we can actually get a pretty good estimate for the true ground state energy given just a double excitation ansatz. Today, what we're going to do is improve a little bit what we did yesterday. We're going to talk about the importance of initial state preparation, and this is true generally for any quantum algorithm or any hybrid quantum algorithm that you're interested in. The idea is going to be, while the Hartree-Fock state is usually a good place to start, there are other methods that can improve on that initial reference state and can improve the workflow of your algorithm. Yesterday, I also mentioned various applications of ground state energy estimation. One of the ones we're going to look at today is reaction rates and chemical reactions. We're going to look at 2 examples of chemical reactions. Very simple ones, but it kind of lays the foundation for more advanced applications. And then, I don't think we'll have time, but if we have time, we'll look at something called penny lane data sets. If we don't have time today, then we'll look at that on Thursday. So, the initial state preparation, what we're going to do today is actually coming out of work that the algorithms team at Xanadu was involved in directly. The idea is just about any quantum algorithm applied to quantum chemistry for ground state energy estimation needs a strong starting point of where, or to get you as close as possible to the true ground state of your system. And what we're going to do today is combine penny lane with the PySCF library, which is a quantum chemistry, computational chemistry library, to try to improve or build a better initial state. And we'll see that that's going to improve the amount of resources that we need to run VQE. So to give you a little bit of an analogy of what it is that we're looking to do exactly, there's this story, I don't know if it's true, might be fictional, but apparently in 1968, during the Cold War, the US had a nuclear submarine that was following a Soviet ship. When all of a sudden the US lost track of this nuclear submarine. They knew it was somewhere between Virginia and the Azores Island, which is about almost 3,000 miles distance. You can imagine the search area was huge. It must have been tens of thousands of square miles. In the Atlantic Ocean, no less. So If they went into this problem blindly, they would have had an enormous search area to cover to try to localize this nuclear submarine. And you can imagine, with it being a nuclear submarine, the stakes were very high. It was a very important problem to try to solve very quickly. To simplify this problem, they brought in a team of experts, in this case, statisticians. And doing some statistical analysis, they were able to lower the search area to about 300 square miles based on the last radar readings that they had of the nuclear submarine. So they went from something tens of thousands of square miles in search area to a much lower area where they knew they had to look for it. With this help from subject matter experts, essentially, they were able to localize the submarine very quickly and with significantly less resources than if they had to search the entire area. So, what does this have to do with quantum chemistry? Does someone want to venture a link between this analogy and initial state preparation? Yeah, exactly. So you can think of it as your true ground state is the nuclear submarine you're trying to look for. If you go into it blindly, without any subject matter expertise in quantum chemistry or in the molecule that you're looking at, you're essentially facing this problem of looking for your ground state in a very large area of or volume of your Hilbert space. With a little bit of expertise in quantum chemistry and in the problem you're trying to solve, you can lower the search area to a much more confined volume of the Hilbert space and probably be more successful at getting very close to the true ground state. Of course, there are always approximations in every method, so you won't ever really get the true ground state, but you can get arbitrarily close depending on how many resources you're willing to put into the problem. So yesterday, I showed you this diagram that basically shows a range of computational chemistry methods that have been developed as a function of basis set size. So the larger your basis set, the more complex your method, the more exact your calculations would be at the cost of increased computational resources. I told you as well that typically we start with the Hartree-Fock state and then use that as a reference state for the VQE algorithm or whatever algorithm you're looking to run. There are certain cases where you can afford to spend a little bit more time and money and use one of these more advanced methods to build a better reference state. And that's what we're going to look at today. We're going to build a better reference state than the Hartree-Fock state and look at what it does to our VQE workflow that we did yesterday. So what you're trying to optimize ultimately, if you knew your ground state, your true ground state, you want to maximize the overlap between your guess or your reference state and the ground state, the true ground state. The Hartree-Fock gets you really close for relatively simple molecules. The more complex the molecule, the less well your Hartree-Fock state is going to approximate it. So obviously you need better methods. What we're going to look at today are two different methods. We're going to look at something called the configuration interaction with singles and doubles. All this basically does is it starts from the Hartree-Fock state, so you're still always starting with Hartree-Fock, and you're basically adding additional spin orbitals. A little bit, you're adding some mixtures of more different configurations of spin orbitals, kind of like what we did with our ansatz. We're also going to look at something called the coupled cluster with singles and doubles. The idea here is to increase or account for more of the electron-electron interaction, so more of the correlations in your molecule. We're not going to go into the details of the implementation of this. This is what we're going to use the PySCF library for. It's going to run these two methods in the background just by calling a couple of simple functions. All right, so if you've downloaded the notebook, we'll move over to the coding part. And we'll try this out. Okay, so the notebook should look something like this. As before, I've put additional information that you can explore later on in the school. To start, we once again need to install PennyLane and PySCF in the Google servers that we're accessing. This will take a couple of minutes. Not a couple of minutes, a few seconds. Maybe a minute. Okay, once that finishes running, we'll just start running this so it goes when it's ready. We'll import PennyLane and NumPy's version of PennyLane. So what we're essentially going to do is run the VQE algorithm that we did yesterday using these three different initial state preparations. We're going to compare Hartree-Fock to the CISD to the CCSD. So this one has more details, just so we don't spend time coding every single line. This first step is going to create the Hartree-Fock state. It's in a slightly different format than yesterday, just because we're going to need to interact with the PySCF library. So you can go ahead and run this cell as well. So we've created the Hartree-Fock state. We want to create this CISD state. And the way we're going to do that, we're going to do it for the H3 ion this time. So not quite the same problem, not that H2 molecule, but the H3 ion. In this case, we are going to define the interatomic distance between the hydrogen atoms as 1.2 atomic units. To create a molecule in PySCF, just bear with me for a moment. I have to change the keyboard. So we need to define the symbols once again. The coordinates, so the first hydrogen atom we're going to place at the origin. I'm going to do something similar with the other one, so H. The other one, we're going to put a distance R along the z-axis. And then the third one. Good. And then because we're dealing with an ion here, we also have to specify the charge of the ion. In this case, it's got a +1 charge. We're going to feed the Hartree-Fock state to pi-SCF. Okay, and then if everything went well, let's hope I did everything right. It's hard to see from here. Okay, so what we've done here then is create our Hartree-Fock state, create our CISD state. You can see it's already got an estimate for the energy of the CISD state. It also gives you this value called the correlation energy. This is energy associated with entanglement that is not captured by your initial state at the moment. So it's a difference between the true ground state energy and the energy you're estimating with your state. We'll do the same thing for the CCSD. That seems good. And CC. Okay, and I'm just going to add this for visualization purposes. Okay, so we've created our CCSD state. If you want a state vector representation, it looks something like this. If you don't understand the state vector representation, don't worry too much about it. It's just to show you that it differs from the Hartree-Fock state that we saw. Okay, so now we're going to start setting up the VQE algorithm. This time we need to redefine the molecule in a way that Penny Lane understands. A little bit more. Good. Don't worry about this print statement. You can skip that print statement. Okay, so here we again need to define our molecule. So we need to give it the symbols, which are 3 hydrogen atoms. Define the geometry. oh, hold on. I need to change this a little bit. So this number that we're dividing by is the bore radius. It's just to change the units, basically, that we're working on. And we'll create our molecule object. And then finally, get the Hamiltonian and the number of qubits that we need. Okay, so far we've just done the same setup that we did yesterday, just for a slightly different molecule. We're going to define a few more variables that are going to be useful to us in a little bit. We're going to define the wires that are going to go into our circuit, so the range of qubits that we're going to use. The number of electrons in our molecule. How many electrons are there in the molecule? Yeah, there's 2. And we need to define the number of orbitals. How many orbitals do you think that there are here? 3. So the number of orbitals is the same number of qubits that we need to specify the Hamiltonian. So in this case, it's going to be 6, but we already saved that number into a variable, which is the qubits variable over here. Because we're working with a more complicated molecule, we're going to build a different ansatz than we did yesterday. We're going to take a brute force approach and create all possible excitations. So all possible single excitations, all possible double excitations, and just optimize all of those parameters. The way you do that in Penny Lane, we have a method called excitations that takes as input the number of electrons and the number of orbitals relevant to your problem. And then we're going to need the total number of excitations, and this will become clear in a little bit. We're going to look at what all of the excitations are. The way we're going to do that is we're going to print out this variable excitations. Okay, so all we've done so far is built our molecule, built our Hamiltonian, start to set the ground for the ansatz that we're going to use. And if everything went well, you can see all of the excitations here. So this is a single excitation linking the first orbital with the third orbital, one linking the first orbital with the fifth orbital, and so on. And then these ones that have a length of 4, these are your double excitations. So we're ready to run VQE now. The first one we're going to do is just with the Hartree-Fock state because it's a slightly different problem. And then we're going to do it for the other 2 states. the first step, if you remember, is we need to choose a device that we want to run the algorithm on. So we'll use the default.qubit device, and we need the number of qubits that the molecular Hamiltonian estimated we're going to need for this problem. We'll define a Q node that's going to link our device with the quantum circuit that we want to run. So we'll call that, that circuit VQE. It's going to take some parameters that we'll call theta and some initial state. So we're trying to make this a general circuit so that we can feed it the Hartree-Fock state, then the CISD state, then the CCSD state. I guess this should be here. So the first thing, what's the first step? What's the first thing we need to do in our circuit? Sorry, I think someone said it. One more? Yeah, we need to encode the basis state into the circuit. Just give me a moment. Okay, it deleted one thing, so let me just do that again. So here, we're going to build the ansatz here. The way we do it, it's a little bit, let me just copy it to speed things up. So the way we build our ansatz is we take all of the excitations that we created here and we add them to the circuit one by one, essentially. So we're looping over all of the excitations that we created. If that given excitation has a length of 4, that means that it's a double excitation. So we'll call the double excitation function with a given parameter acting on specific wires. If it's not of length 4, that means that it's a single excitation. It's going to take a different parameter, and it's going to be applied to a different set of qubits. And we'll see what that whole circuit looks like in a little bit. And then what we want to return, remember we're looking for energy. So we want to return the expectation value of our Hamiltonian. Hopefully everything went well. Oh, hold on. I think I have to. Oh, maybe it didn't. Okay. So speeding things up a little bit, we're again going to define an optimizer. And we're going to print out the circuit. So remember, if you want to print out the circuit and you have parameters, you need to give it values. You need to give those parameters some values. In this case, it doesn't matter what they are, so we're just going to take all of the parameters to be 0. We need a number of parameters equal to the number of excitation gates that we have. And we want to make this differentiable. Yeah, that should be good. Okay, and if everything went well here. Okay, so this is what our circuit looks like. You can see it's already more complex than the one we did yesterday. So this first one is encoding your Hartree-Fock state into your circuit. And then you have a series of single and double excitation gates that are acting as your ansatz. Keep in mind that this is a brute force approach. You're trying to create the most general superposition of states that you can. If you have a little bit more insight into the problem, you might be able to remove some of these. But here we're just trying everything possible. Here? Yeah. I guess, any questions so far while we wait? So far, so good. What do you think is going to happen, by the way, with the new initial states? What do you expect to see? So if you're closer to the true ground state, what's one possible benefit of this? Sorry? Yeah, we're going to see that we're going to need less number of iterations in our optimization, essentially. So let's try it out. New energy. Oh, I need this one. So this is just running the same thing that we had before. So let me just type it out and then I'll explain. So far the workflow is essentially the same. We've chosen our optimizer. We're going to take an optimization step with the current set of parameters and the Hartree Fock as an initial state. We're going to save the new energy estimate after one round of optimization, calculate the change in energy, and print every 5 iterations what the result is. And if I did everything correctly. Okay, so I want you to keep this number in mind. With the Hartree Fock state, it took 31 iterations to reach convergence of the ground state energy. This one is pretty much the same, so I'm just gonna copy it over. I'll eventually share these notebooks with the organizers so that they can post it on the website and you can have access to this. Wait, there's something weird here. Huh. Okay, there's something a little bit off, so let me just show you what it should look like. So what you should get is with Hartree Fock, it takes 31 iterations until you reach convergence. With the CISD and the CCSD, they both take about 16 iterations until convergence. So by preparing a better initial state, you've reduced the number of iterations you need by about half, which in this case, it doesn't matter too much, it's only 16. But if you're looking at a difference of 1,000 iterations and 500 iterations, it starts to become an important factor. And then if you do this, oops. You can plot the same thing that we did yesterday. So the energy estimate as a function of number of iterations. The red line here is what we saw yesterday using the Hartree Fock method. And you can see with the other two initial states, we already start much, much closer to the true ground state energy. And it takes less iterations to reach convergence. So the moral of the story here is sometimes it pays off to spend a little bit more time at the beginning, prepare a better initial state so that your quantum algorithm is more performant. All right, any questions about this? Yeah. Yeah. It depends. CCSD is the more expensive one, so you'll get more. If you can afford it, you get more, better results out of it. So it depends on the size of the molecule and how many resources you can spend. If you can afford CCSD, it's usually better. If you can't, then CCISD is still better than Hartree Fock. Okay. So going back to the presentation, we're going to change topics a little bit and start talking about chemical reactions. Okay, so this is just summarizing the results of this demo. If you can afford to spend a little bit more time preparing a better initial state, you'll see that you get better performance generally. If, as an exercise, what you can do is calculate the overlap between each of these states, the overlap being just the inner product of your different states, and you'll see how well they overlap. The Hartree-Fock state and the other two states actually overlap pretty strongly. You'll get an overlap of about 0.9. Ideally, if it's perfectly aligned, if they're parallel states, you'll get a value of 1. So for the H3 ion, Hartree-Fock is actually not too bad. But as the molecule gets more complex, that overlap is going to decrease. So as an example application, we're going to look at a couple of very simple chemical reactions. The way that we're going to study these reactions is using something called potential energy surfaces, which I think probably most of you are familiar with, but in case you're not, we'll quickly review them here. The idea of a potential energy surface comes essentially from what's known as the Born-Oppenheimer approximation, which I kind of alluded to yesterday. The idea is because electrons and nuclei are so different in size and mass, for certain cases, you can completely decouple the degrees of freedom of the nuclei and the electrons in your molecule, treat them as two independent wave functions, completely ignore the wave function of the nuclei, essentially, because everything that happens with them, if you make a change in the configuration of the nuclei, the electrons are going to respond to that really quickly. So you can essentially ignore that response. And you can come up with this idea of an electronic energy as a function of nuclear coordinates. What we're going to do to build this potential energy surface is we're going to look at the case of H2 dissociation. So we're going to gradually separate the hydrogen atoms, start off at some distance, vary that distance, and we're going to build a graph that looks something like this. The energy that we looked at yesterday with the weird numbers that we took as coordinates, they were the coordinates that will get you somewhere around here, close to the equilibrium position of the atoms. Okay, so this dissociation of H2 is basically the reaction of starting from an H2 molecule and gradually pulling apart the hydrogen atoms until the bond breaks. The idea is going to be to run VQE for different distances of the hydrogen atoms and gradually build up this potential energy surface. Once you've come out of this kind of potential energy well, that means that your atoms have completely dissociated. How do you think you can estimate the amount of energy you need to put into the system to dissociate this molecule? Yeah, so if you start with your molecule in equilibrium, you want to compare the difference between the energy it has at equilibrium and the energy it has somewhere around here, where it's left the potential energy well and it'll no longer come back together by itself. Anywhere in between here, in principle, you can think of it as a ball rolling down a hill. If it's somewhere here, it's going to be able to recover from that stretching. It might oscillate a little bit, but eventually it'll fall back into equilibrium. Okay, so what we're going to do is estimate this electronic energy as a function of nuclear coordinates using VQE. I believe I left most of the code, so there will be less code to write this time. going back over here. Okay, so to do this, we are going to just start off from the Hartree-Fock state. If you want, you can try this again with the other two states, the other two methods. So here, we're trying to encode the total number of electrons in our system. We have 2 hydrogen atoms, so that means that we'll have 2 electrons. Oops. Yesterday, we saw that we're going to need 4 qubits or 4 orbitals for this. Actually, let me define orbitals here. And then again, build up our molecule. So this one, let me just see. Yeah, so we can run this cell over here. Oops. This one should be able to run. So what we're doing here is we're going to take a range of separations between the 2 hydrogen atoms. We're going to start from a distance of 0.5 atomic units, go all the way to 5 atomic units in steps of 0.25. We're again going to look at a different ansatz, so we're going to create all possible excitations in this case. And we're going to do VQE essentially at each one of these distances. This one, this is going to take a while, so let me just... In the interest of time, I'll just do it like this. What our circuit is going to look like if everything went well. Okay, you can see our circuit looks a little bit different than it did yesterday. We've now included the 2 single excitation gates. So remember, you have, you start off with the 1100 state. Yesterday, we only took into account a superposition of that state with the 0011 state. This time around, we're just brute forcing it and including the other 2 states. And what you get at the end is the potential energy surface for the dissociation of H2. So you can see it looks very much like the cartoon that I showed you earlier. At each point here, we use VQE to estimate the electronic energy for different bond lengths. And then you can just run this cell. And you can see here we have an estimate for the equilibrium bond length. So this is essentially the value we used yesterday. And you can get an estimate for the dissociation energy, which is about 0.2 Hartrees. Okay. Again, it's a simple toy model, but these potential energy surfaces are very useful for other chemical reactions. We're going to look at another one where it's a more complicated reaction that is going to have 2 potential energy wells. One of them is going to describe the reactants. The other set is going to describe the products of your chemical reaction. Any questions about it so far? Yeah. Yeah. Yeah, you can include it. And actually, once I share the proper notebook with the solutions, you can try it out with the other methods and see the difference. Okay, so the other reaction we're going to look at is a little bit more complicated. It's still one of the simpler reactions, probably the simplest reaction. We're going to look at the hydrogen exchange reaction, which involves an H2 molecule with a hydrogen atom. We're going to pull apart the hydrogen molecule until one of the hydrogen atoms bonds with the other one. So you're not really doing very much of interest. You're really just taking what was an H2 molecule, transforming it into a hydrogen atom. The one that was the hydrogen atom is going to turn into the H2 molecule. To understand what the way that this is kind of abstractly thought of, and this is true of any chemical reaction, the potential energy surface of chemical reactions typically looks something like this. You'll have two local minima in your potential energy surface. They are separated by some kind of potential energy barrier that the reaction needs to overcome for it to run. This is an abstract representation. The axis here is the reaction coordinate. The reaction coordinate can sometimes be a very abstract quantity. In our case, what do you think the reaction coordinate is going to be? What's going to dictate the extent of the reaction for us? Yeah, exactly. So for us, the reaction coordinate is happily a very familiar one. It's a geometric distance between the hydrogen atoms. The activation energy for any chemical reaction is the difference between the transition state, which is typically a kind of mid-level configuration of your molecules at the top of this potential energy hill, and the energy of the reactants at equilibrium, so the value over here. The way that you can extract a chemical reaction rate from this activation energy is given by a relationship known as Arrhenius' equation, which says that the reaction rate of any chemical reaction depends exponentially on this activation energy relative to the thermal energy scale of your problem. So what that means and what's kind of intuitive about it is reaction rates are dependent on temperature. You know that typically if you want to slow down a reaction, you lower the temperature. If you want to increase its rate, you increase the temperature. One important consequence of this in terms of kind of computational methods is because the reaction rate depends exponentially on the activation energy, small errors that you make in the activation energy can have very important consequences for the reaction rate that you estimate. If you're off by 10% in your activation energy, you could be off by quite a bit in your reaction rate. And we're going to see an example of that with the hydrogen exchange reaction. All right, any questions about it? Is the setup clear? Good, okay. So for this one, we're going to need a couple of additional libraries to help us out. So once we've installed those libraries, it's the same workflow. Essentially, we're going to define our molecule, create our ansatz, and do Hartree-Fock to recreate this potential energy surface. Do you guys want to try it out on your own, the first step, building the molecule, the Hamiltonian, or do you want to go through it together? So who votes for going through it together? Who wants time to try it out on their own? Okay. Yeah. So the molecules that we're interested in, or the total atoms that are involved in a reaction, are 3 hydrogen atoms. In this case, we're going to add an extra parameter called the multiplicity. By default, Penny Lane builds up the molecule assuming a multiplicity of 1, meaning that all electrons are paired. In this case, because we have an unpaired electron, the multiplicity of all the atoms or all the molecules is 2. That's explained very briefly over here. Okay, so multiplicity is the number of unpaired electrons plus 1. If you don't have any unpaired electrons, multiplicity is 1. In this case, we have 1 unpaired electron as we separate the hydrogen atom, the 2 hydrogen atoms together. So we need to account for that by defining the spin multiplicity as equal to 2. So how many electrons do you think we have in this problem? Yeah, we have 3 because it's no longer the hydrogen, the H3 ion, it's just 3 hydrogen atoms. We're still going to need 6 orbitals. And as our ansatz, we're again going to create all possible excitations. To keep things simple and to make sure that the code runs this time, we'll still start with our Hartree-Fock state. But again, I invite you to try out the other states and see the difference. And then we'll choose the optimizer. Because I've tried this before, I know that a step size of 1.5 happens to work pretty well. And then we'll run this for at most 60 iterations. There's going to be an error. Okay, so the workflow now is basically the same as we did for the H2 dissociation. We're fixing 1 hydrogen atom at the origin, another one at a distance of 4 atomic units away, and we're going to vary the distance of the middle hydrogen atom over a range of values. So we are going to, again, define our molecule. defining our Hamiltonian, this is where we're going to need the help of open fermion. So we feed it our molecule object as before. This time we're going to ask it to use open fermion's method to construct the Hamiltonian. The reason for that is just because at the moment, the penny lane library doesn't support molecules with multiplicity greater than 1, whereas open fermion does. All right, any questions so far? Good, okay. So we're going to create the VQE circuit. The optimization, I think, is already set up, so this shouldn't take too long. Rather than, so we built all of the excitations like we did before. Rather than building a for loop and identifying the double excitations and single excitations, we're going to use a template. So a built-in template that PennyLane has to facilitate this kind of workflow. Template. Okay. So this template is going to do the same thing that we did earlier here. It is essentially doing this part. So it's adding all of the excitations that we created to the circuit, but in a much more efficient way. Back here. We need to give it as input the parameters of all of the excitations. The range of orbitals, so the range of qubits that all of these excitations are going to act on. Our initial state, which is going to be the Hartree-Fock state. And the list of single and double excitations that we're going to need for this circuit. And I believe that's it. All singles, double. Oh. Oh, templates. Okay, this one is actually going to take a little bit of time. What we're doing here, remember, is building up this potential energy surface of taking a hydrogen molecule with another hydrogen atom close by and ripping one of them apart and putting the other one together. We can actually visualize the circuit once it finishes running. An important thing to notice is the way that we defined our molecule. It's very similar to how we defined the H3 ion. We defined all of the symbols involved. These are a delineation of all the atoms involved in the reaction. It's not just the molecules themselves. This should finish soonish. Okay, so the way that our circuit looks like now, this was a question I got yesterday. If you know that the Hartree-Fock state is set by a number of electrons that you have, why don't you just do poly X gates? And that's exactly what the basis state preparation does for the Hartree-Fock state. And then we have all possible combinations of excitations. So all double excitations possible, all single excitations that are possible. In practice, you don't really do this. There are methods that are adaptive. So you can use all singles and doubles, calculate the gradient of your circuit if you're optimizing it, and discard the gates that have a very small gradient so that they're not contributing very much to your optimization, and reduce the number of gates in that way. We'll talk about gate fidelities a little bit tomorrow and the importance of reducing the number of gates that you use. This doesn't look like a lot, but keep in mind each of these double excitation gates are composed of various single and double qubit gates. So lots of poly gates, lots of C0 gates. If you can remove any amount of these, it's always beneficial. If we did everything right, this should look like, yeah, something like this. So first thing, as a sanity check that we can do is, why do you think that this potential energy surface is so symmetric? It looks quite a bit different from this picture that I showed you. Typically, the reactants are, maybe not typically, sometimes the reactants are at a higher energy level than the products. Sometimes it's the other way around. In this case, both the reactants and the products are at the same energy. Yeah, the reason, of course, is because you haven't really done much. Your reactants are essentially the same as your products. All you've done is interchange two hydrogen atoms, or exchange a hydrogen atom. What we can do then, and what this next part of the code does, is it's going to calculate the energy difference between your transition state. So this is somewhere between a massively deformed hydrogen molecule and a hydrogen atom that's trying to attach itself to the semi-loose hydrogen atom. Okay, the number maybe doesn't mean very much to you. The way that these are typically interpreted is these values are computed up to what's known as chemical accuracy. How many of you have heard about chemical accuracy before? A few of you? Okay. Can you explain it? No? So chemical accuracy is basically a standard that the computational chemistry community tries to stand by, that any computational result that you get has to match with the precision that you have in experiment. In experiment, you can typically reach chemical accuracy. Any computational method has to match that accuracy. It's not always the most relevant scale. It depends on a lot of factors, but it's kind of a general standard. We can also compare this activation energy to thermal fluctuations. Why do you think that will be important? What happens if the activation energy is, let's say, less than the energy scale of thermal fluctuations? Yeah, you would have essentially a spontaneous reaction that just by the bumping of other molecules, you can have this ripping apart. So that's sometimes an important result to measure, whether your reaction can be spontaneously just created by the environment. In this case, we're going to take room temperature. Most chemical reactions don't happen at room temperature, so it's always important to make this comparison at the right scale. At high temperatures, you might have a spontaneous reaction just because of thermal fluctuations. We're also going to explore a little bit what I talked about, that if you're off in your activation energy by 10%, how much will that affect your reaction rate? So if we do this, in hard trees, which may be a bit of an unfamiliar scale to a lot of you, the energy scale of thermal fluctuations is about 9 times 10 to the minus 4 hard trees. You can see the activation energy is about an order of magnitude bigger than that. So this reaction doesn't really happen spontaneously just due to thermal fluctuations. You need to input some energy to actually pull the hydrogen molecule apart and create the other one. What do you think this number means? So here we calculated the ratio of reaction rates. So we computed the reaction rate for one activation energy. We recomputed it for an activation energy that's 10% lower than the other one and calculated the ratio of those two rates. That ratio comes out to be about 0.02. How would you interpret this number? This is the ratio of two different estimations of the reaction rates, one of them taking the exact activation energy and the other one taking 10% of the activation energy. So you're assuming that you have an error in your calculation. That means that your activation energy is 10% what it should be. And we're trying to figure out what the consequences of that error is in our estimate of the reaction rate. So how would you interpret this number, this 0.02? It is pretty great. It's a factor of 50. So if you make a 10% error in your activation energy, that translates to a factor, you're off in your reaction rate by a factor of 50. So you can see that this exponential dependence holds kind of a cautionary tale in terms of precision of computational methods. You need to try to be very accurate in your computations when you're doing something like estimating reaction rates, because that can make the difference between expecting that a reaction is going to happen in 1 hour versus happening in a minute, for example. All right. So I think we'll stop here. I don't want to rush the idea of penny lane data sets, but to kind of preview for tomorrow, what data sets are, it kind of goes to a question that someone posed yesterday of when we load molecules, when we load Hamiltonians, is all of that information stored in penny lane or are we recalculating it each time? The answer to that is the way we were doing it, we're recalculating it each time. Naturally, that's not always the best type of workflow. If someone has done the work before, there's no reason why you need to do it again. So just like kind of the machine learning community has data sets that are kind of ready to use, penny lane also has a range of data sets for different molecules and spin systems and machine learning problems that other people have created. They've gone through the trouble and spent the time and resources to do a lot of these computations, and you can just load them directly from some database. And the hope of that is to lower the time to research. So you don't have to spend time recalculating ground state energies. If someone else has already done it, you can use that result and build up on it to apply it to the problem that you're interested in, essentially. So that's what we'll talk about tomorrow at the beginning. And we'll also look at a slightly different application of variational quantum algorithms for quantum chemistry. We're going to look at one particular variational algorithm that's going to help us estimate excited state energies. So the ground state is very important. Excited state energies have a different range of applications that are sometimes of interest. All right? Yeah, so that's it.